Good morning. We are going to start electrochemistry. We have two units of electrochemistry in our syllabus, Unit 5 and Unit 6. We are going to start Unit 5 electrochemistry 1. In this, we are going to study the mechanism of electrolysis, how the conduction occurs in metal and in electrolyte solution. We will see how it can be measured, Arrhenius theory given for the ionization and the migration of ions, then the transport number, its definition and the determination, Kohlrausch law, its different applications, then the conductometric titrations which are having various applications in the titration of strong acid, strong base and all the four combination, precipitation titration, conductometric titrations, Ostwald dilution law, and then we will see the theory generated for strong electrolytes, that is Debye-Hückel-Onsager theory. So, after this unit, you will be able to learn how the chemical energy can be related to the potential, electrochemical potential. From the sign of the potential, we can predict the direction of the reaction. We can define the standard state and why it is necessary to define it. Also, the various components of electrochemical cell and the purpose of each and the process of occurring it. We can write down effectively the electrochemical cell, the various processes responsible for the conduction of electricity, and whether the chemical reactions and electrochemical reactions are reversible or irreversible. So first of all, what is electrolysis? The word electrolysis, electricity means flow of electrons, pertaining to flow of electrons, electrolysis. Actually, electrolysis conduction can be in metals or electrolytic conduction. Now, what happens when the conduction occurs in the metals? Metals, best conductor of electricity. They remains unchanged with the passage of current. They behave as if it contains electrons which are relatively free to move. So electrons are considered as a charge carrier in metal. Therefore, these conductors are also called as electronic conductors. Metallic conductors, it is the property possessed by the pure metal or alloys or some of the oxides. They allow electric current to pass through it. And electrolytic conductors through which passage of electric current results in actual transfer of matter, or they bring about a chemical change in them. These are called as electrolytic conductor or electrolytes. Electrolytes are of two types. In the first category, electrolytic conductors which conduct electrolytically in the pure state, such as acid, base, salt in water. When they dissolve in water, they conduct the current. Or in the second category, electrolytic conductors which consist of solution of one or more substance. So, generally, electrolytic solutions are prepared by dissolving salt, acid or base in water. Now, the cell, it contains water solution of electrolyte in which we dip two metallic rods. We call it as electrode. These rods are connected to the two terminals of the battery, which is a source of electricity. The electrode connected to the positive terminal must attract the negative ions, and the electrode connected to the negative of the battery attracts the positive ion, known as cathode. Now we will see how the mechanism of electrolysis is. The process of electrolysis actually takes place when the cations migrate to the cathode and form the neutral atom by accepting the electrons. Anion migrate to the anode and yield a neutral particle by the transfer of electrons. As a result of this loss of electron by anion and gain of electron by cation at their respective electrode, chemical reaction takes place. Now, about the conduction, the passage of current through the solution of salt results in the electrolysis. Now, when we think about the conduction process, then the electrolytes, they obey Ohm's law to the same extent as that of metallic conductor. According to this law, the current I, which is flowing through the conductor, it is given by I is equal to E upon R. E is the electromotive force. That is the difference between the potential at the two ends of the conductor. R is the resistance. The different electrical units which we should understand before going deeply in the unit: ampere. These all terminology you have studied in the 12th standard. Ampere, it is the current strength expressed in ampere, defined as current which deposit some 0.00118 gram of silver per second from a 15% solution of silver nitrate, suppose, in a colorimeter. Or it is an ampere, it is a current of 1 coulomb per second. Now what is coulomb? The quantity of electricity passing through a conductor, it is a product of current strength and the time, generally expressed as coulomb. Ohm, ohm is the unit of electrical resistance. Resistance offered to 0 degree Celsius to a current. Volt is a unit of EMF, electromotive force. It is the difference between electrical potential required to send a current of 1 ampere through a resistance of 1 ohm. Then Faraday's put three laws. Faraday's law of electrolysis. There are two laws. One is first law of electrolysis, the amount of given product liberated at an electrode during electrolysis, it is directly proportional to the quantity of electricity passed. And what about the second law? When the same amount of electricity passes through the solution of different electrolytes, the amount of substance liberated at the electrode are directly proportional to their chemical equivalent. So these two laws hold good very rightly, provided the passage of electricity takes place entirely by the electrolytic conduction. So now we will see the verification of the second law of electrolysis. Now Faraday's law, second law states that when that quantity of electricity is passed through different electrolyte solution, the masses of substance deposited on the electrodes are proportional to their chemical equivalence. To verify this law, let us take this arrangement. Now pass some amount of electricity through the 3 colorimeter containing the solution of dilute sulfuric acid, copper sulfate, silver nitrate. These colorimeters are fitted with a platinum and a copper and silver electrodes as shown in the figure. The masses of hydrogen, copper and silver liberated at the respective electrode are found out in the ratio of their equivalent weight. So we can find this formula: mass of hydrogen liberated upon mass of copper deposited is equal to equivalent weight of hydrogen upon equivalent weight of copper, or mass of copper deposited upon mass of silver deposited is equal to equivalent weight of copper and silver. So from this experiment we can calculate the mass of hydrogen, copper, silver deposited at their respective electrode by 1 coulomb of electricity. Since the equivalent weights are known, that is 131.78 and 107.88 for silver, it follows that electrochemical equivalents are proportional to chemical equivalents, or it is proportional to equivalent weight. Now, after this, we should know that flow of electricity through the solution of electrolyte, it is due to the migration of ions. When potential difference applied between the two electrodes, the power of electrolytes is formed conductance. It is defined as the reciprocal of resistance. Like metallic conductor, electrolytes obey Ohm's law. According to this law, the current flowing through the metallic conductor is given by I is equal to E by R. Now, If we remove the if R is taken as a resistance, then it is proportional to the length and inversely proportional to the area of cross section. So R is proportional to L by A. If we remove the proportionality sign, we introduce the term rho. Rho is the specific resistance of a conductor. Rho, specific resistance. So if rho is a specific resistance, then surely 1 by rho will be specific conductance. Now we will see what is specific conductance. Now specific conductance, we know that this is the formula for resistance. If L is 1, A is 1, then this resistance becomes equal to resistance. Specific resistance is nothing but the resistance when the length is 1 and area of cross section is 1 square centimeter. So this is specific specific resistance, and its reciprocal is specific conductance. We can find out the unit also, that this specific resistance means and R into A upon L, and the inverse of it will be specific conductance having unit ohm inverse centimeter inverse. Ohm inverse centimeter inverse. Ohm inverse is mho. We can call it as mho. The specific conductance increases with ionic concentration and the speed of ions concerned. Now the next is equivalent conductance. Now equivalent conductance is the conducting power of all the ions produced by 1 gram equivalent of an electrolyte in a given solution. It is the conductance of 1 gram equivalent of electrolyte only. And about the molar conductance, molar conductivity, it is helpful in comparing the conductance of electrolytes. It is defined as the conductivity of a solution of 1 mole of electrolyte when it is placed between the two electrode 1 centimeter apart. So this is for 1 gram equivalent electrolyte. This is for 1 mole of an electrolyte. So this we have to remember. Now the next is how to measure the electrolytic conductance. Now conductance, reciprocal of resistance. So if we measure the resistance of the solution, it will be helpful to determine the conductance. And resistance can be successfully measured by Wheatstone bridge. The solution whose conductance to be measured is kept in the cell which is shown here. The solution, suppose we have to measure the conductance of this solution, we have to make the arrangement like this. And after that, for measuring the resistance, we have to arrange the Wheatstone bridge. Now, the vessel in which conductivity of the solution is measured, it is known as conductivity cell. Now, the electrodes are polarized, that is the product of the electrolysis accumulate on them, and the passage of current involves decomposition of the solute. Now, the arrangement is made like this. The conductivity cell is attached to the bridge. This is known as Wheatstone bridge. The sliding contact, this one. The sliding contact, it is moved slowly along the wire AB till we reach a point X. When we reach at this point, then the potential becomes equal to R. Under such condition, no current will flow through the headphone and it will be silent. Sometimes there will be the reflection of light, sometimes there is some voice, some tone. There are different types. At all other points, a buzzing sound can be heard in the headphone. In actual practice, it is not usually possible to obtain complete silence in the headphone. So the point of minimum sound, we take it in the experiment. And what is the successive calculation? Resistance of C upon resistance of R is equal to this is R C, which we want to find out. So resistance of C upon resistance of R is equal to resistance of Bx, means the length of Bx, is equal or divided by resistance of Ax, means length of Ax. So we can calculate the resistance as equal to the ratio of both the length multiplied by this resistance. So after determining the specific resistance, the equivalent conductance, molar conductance can be easily found out. Now the cell constant. How to determine the cell constant? Now, this exact value of cell constant can be determined by measuring the distance between the two electrodes and the area of cross section. But we know that it is very much impossible to measure the actual dimensions. So an indirect method is specific conductance is equal to observed conductance into cell constant. So we can find out the cell constant as the ratio of specific to observed conductance. To determine the cell constant, a standard solution of KCl whose specific conductance is known, it is used. Then the solution of KCl, it is prepared of known strength and its conductance is determined experimentally, which is observed conductance. Theoretical value of specific conductance can be found out from the literature, and from the ratio of both we can find out the cell constant. This we actually do in the laboratories. Now we will see how there is a variation in molar and specific conductance with dilution. What happens to the molar, specific, equivalent conductance when we dilute the solution? With dilution, following variation occurs. Value of molar conductance increases on dilution. So how and why, we will see it in detail. Effect of dilution on molar conductance. Both the conductivity and molar conductivity, they change with the concentration of electrolyte. Conductivity always decreases with decrease in concentration for weak and strong electrolyte. Conductivity decreases. This can be explained by the fact that the number of ions per unit volume that carry the current decreases on dilution. The conductivity of a solution at a given concentration is the conductance of 1 unit volume of solution kept between the two electrodes. So molar conductance, so with dilution the value of molar conductance increases on dilution. The increase is due to the fact that molar conductance, it is the product of specific conductance and the volume containing 1 mole of electrolyte. As the decreasing the value of specific conductance, it is more than compensated by increasing the volume V. So molar conductance increases. When we talk about the molar conductance with dilution means towards 0, it increases surely. Molar conductance at different dilution, it is plotted for different strong and weak electrolytes, and it has been observed that the value increases. Now what happens to the specific conductance? Specific conductance, it is the conductance of 1 cc of solution of an electrolyte. If we dilute the solution, the specific conductance decreases. If we dilute, the specific conductance decreases. I'm sorry, I forgot to take the table for the specific conductance here. The specific conductance decreases. On dilution, the concentration of ions per cc decreases, hence specific conductance decreases. But the equivalent conductance and molar conductance increases. Always remember the point. Equivalent conductance and molar conductance, they increases with dilution. But specific conductance is the conductance of 1 cc of a solution. On dilution, the concentration decreases, and that's why conductance decreases. Means specific decreases, molar and equivalent increases. Because equivalent and molar, they are the product of specific conductance and a volume containing 1 gram equivalent of 1 mole of electrolyte, and the volume is increasing. So with dilution, specific conductance decreases while volume increases. The increase in volume supports increase in the conductance of molar and equivalent conductance, but it opposes the increase in specific. So specific conductance decreases with dilution. Now there are two types of electrolytes, strong and weak electrolyte. So we have to take into consideration of the behavior of conductance for strong as well as weak electrolyte. They behave differently, strong and weak electrolyte. From the graph, it is clear that they behave differently. This is for strong electrolyte. We can see a straight line. But in weak electrolyte, a curve is observed. This is the curve. This line can meet, it can intercept the y-axis, but here we can't predict the intercept of the line. This is for weak electrolyte. This is for strong electrolyte. Strong electrolyte are completely dissociated in solution and hence decrease in concentration or increase in dilution with increase in the mobility. So with dilution, equivalent conductance increases in a regular straight line. At infinite dilution, their value can be extrapolated and we can find out the intercept at infinite dilution. So KCl, strong electrolyte, they can have limiting value at zero concentration. Whereas for weak electrolytes such as acetic acid, there is no indication that a limiting value can be obtained by extrapolating. No, we cannot experimentally determine the molar conductance for weak electrolyte. If we find out experimentally, we will be able to find out these readings only. But we don't know its intercept. So maximum value of molar conductivity, it is termed as molar conductivity at infinite dilution. It can be determined experimentally. If we take these readings, we can get a straight line which can be intersected on y-axis to get the infinite dilution reading. But if we plot for weak electrolyte, we will get such reading, but we don't know the exact intercept of this line. So this is the difference between the strong electrolyte and weak electrolytes. Now the effect of temperature on the equivalent conductance. Equivalent conductance should increase with temperature as with an increased temperature. The dissociation of electrolyte and the ionic mobility increases. So we can find out with this equation. Now, various numericals can be asked in the exam to determine the equivalent molar specific conductance from the given L and A. The problems on the cell constant can be asked. That is only of 2 marks or like that. Now, this is the actual experimental arrangement which we perform in the laboratory. So the points to remember is, as concentration decreases, conductivity decreases for both strong and weak electrolyte. Weak electrolytes have low degree of dissociation as concentration increases. Molar conductivity increases as concentration decreases, means dilution. The variation is different for strong and weak electrolyte that we have discussed just now. And the molar conductivity, we have seen that it's of strong electrolyte, it is weakly dependent, and the molar conductivity of weak electrolyte depends greatly on the concentration of the solution. Now, this is Kohlrausch law, which has been useful for calculating the conductivity at infinite dilution, lambda infinity, which instead in strong electrolyte we were able to find out at infinite dilution, but for weak electrolyte we cannot find out. So that time Kohlrausch law has been used. So this is the effect of dilution on the conductivity, that specific conductivity decreases. You should remember this, that the specific conductance decreases on dilution and the equivalent and molar conductivity increases with the dilution. And the conductance in all the electrolyte, they increases with the temperature. So this is all about the conductance, equivalent conductivity, molecular or molar conductivity, conductivity at infinite dilution, specific conductivity, and their variation with the dilution.